Pietra, and yeah, I'm a software engineer for Embecosm. Today, I want to talk about the very edge of AI, so inference for the smallest processors. So specifically talking about how we can run PyTorch on bare metal microcontrollers. So most of the time we talk about edge AI, we're still assuming a powerful processor, probably running Linux. But there's many applications in small-scale image processing, in audio streaming that could run on much smaller and cheaper hardware, with the challenge of having limited resources. So in this talk, I want to talk about how we adapted a standard PyTorch embedded framework, ExeTorch, to run in a constrained bare metal environment. So what are PyTorch and ExeTorch? Just to quickly define them. Most of you probably know PyTorch. It's a massive open source Python-based machine learning framework. It's great, but it's built for flexibility and power, handling training and inference. Whereas ExeTorch, which is an official extension of PyTorch, is designed specifically for resource-constrained devices. The main difference being that it handles inference only, so the training happens on the big, powerful machines, and then ExeTorch makes it work with your embedded device. So how the models are run. So at a high level, this is what it looks like. We have a neural network represented as a graph. We have the graph evaluator, which goes through the whole graph. And it performs two key tasks. It does the tensor assignment and the operation evaluation. The tensor assignment pretty much being the memory allocation, and the operator evaluation being the actual math, so running convolutions or whatever calculation we need. After that, we have the dispatcher, which then sends the operations to the best available hardware, either the host CPU or the accelerator. And alternatively, we can have a graph-level transformation before that, which can simplify, fuse, or even modify the graph. ExeTorch specifically runs the models like this. It's a very high-level picture, but it does explain it quite well. So basically, we have two phases. We have the ahead of time and the runtime phase. In the ahead of time, we run it in the developed machine, so not on the embedded device. We take the model through PyTorch, then the ExeTorch front end lowers it into a portable format. And the delegate partitioner is still in the ahead of time part, analyzes the graph and decides what part of the models are going to be delegated. So what part of the models we want to run on the hardware, on the host or the accelerator. We're going to run hardware. And then we have the standard runtime, which is the second part of it. That's what runs on the actual microcontroller. So we have the program loader, which gets the model, the PTE file. Then we have the method loader and the executor, which runs the inference, coordinating with the accelerator where things are going to go. And then at the bottom, you can see, as I said before, that the microcontroller is not just one thing. It has a host, which is a CPU 0, as well as other CPUs and custom design hardware. So I've used the term resource constrained quite a lot, but I want to be very specific about what that means on bare metal environments. So yeah, less memory. We're not talking about gigabytes. We're talking about megabytes of total memory and very little fast memory. less compute. We have just a few cores, maybe just a few accelerators. No OS, so there is no Linux, no Windows, no virtual memory, file system, or dynamic linker, which means that everything must be compiled directly into the final binary. We can't load libraries on the fly, so we have to remove all the dynamic lookups and dependencies, and only have direct implementations in that one binary. So optimizations. So the first strategy to optimize it is where do we run the code? Given our hardware model, we classify every operation into 3 different categories so we can have the maximum efficiency. So the first one, we have operations that get delegated to the host. So simple setup operations, or operations that the accelerator just doesn't support. We can delegate to the accelerator CPUs. So we can use it for computationally intensive calculations, but things that are not supported by the custom hardware. And then the most critical, which shows the most improvement in performance, is using the custom accelerators. So for example, it can be a convolution accelerator that, is going to be way faster than just running on the CPUs. And to support all of this, we have to write our own custom operators, often having to have an 8-bit version of it as well as a 32-bit version, so we can choose which is best for each part of the model. So the next big challenge we have is memory. As we saw, we have the main memory, but we also have a small, precious amount of closely coupled memory, which is very fast. We can't just let the runtime put things whatever it wants. We need to place things in different parts of the program, for example, the model weights and the intermediate tensors into the most efficient sections. So we use the fast memory to cache frequently used data, for example, the initial layers of the model, and also the intermediate results. Because AI algorithms can be very predictable, we often just use regular loops, which we can proactively prefetch from the main memory to the fast memory before the processor even needs it. So the single biggest way to save memory that we found is quantization. So in a traditional system, the model's weights and biases are often stored as 32-bit floating point numbers, but this often is overkill and uses a lot of memory. Quantization is the process of converting these numbers to lower precision formats like 8-bit integers, which immediately reduce the size of the model by 4 times on average. But obviously there's a trade-off between the size and the accuracy. But many AI microcontrollers, they have hardware accelerators specifically for quantized maths. So for example, we've seen NPUs that can support 4-bit up to 8-bit operations within the quantization. And our job is to find the optimal scheme. So maybe we can have 4-bit weights and 8-bit activations. So we can find the best balance between accuracy, memory saving, and performance. Yep. So all of this sounds great, but what happens if the hardware you're targeting doesn't exist yet? This is a very common problem in chip design. this is where pre-silicon development comes in. We can't wait for the physical chip to be manufactured, which can take months or years. Instead, we use Verilator, which takes the hardware design, the Verilog RTL, and compiles it into a C++ model. The model is cycle accurate, so it behaves exactly like the final chip, just a lot slower. And as you can see, we can also connect standard debugging tools like GDB and OpenOCD directly to the C++ model, so we can debug the bare metal code just as if we had the hardware. So this pre-silicon model gives us really good analytic capabilities because the model is cycle accurate. We can get a cycle-by-cycle trace of the entire processor state. So here you can see, for example, we have the stack trace, the stack pointer trace, while running the model. And this isn't an estimate, it's the exact stack usage. With this, we can see the peak stack depth and determine the exact amount of RAM to allocate. So for a system that we only have a few megabytes of RAM, knowing this precisely is critical. So yeah, this level of tracing is really helpful for us. And I think I plowed through this. To summarize, we showed 3 key things. So first, ExeTorch can run on bare metal microcontrollers. We can even port it to tiny OS-less environments. To make it work, we need aggressive memory planning, and quantization is essential. You can't just compile and run. You have to manually optimize for memory. And third is that pre-silicon development of Verilator is really helpful, and yeah, it's a huge win. It allows the software and hardware teams to co-develop, so we don't have to wait for anything, saving months of time and resulting in a much better product. So yeah. I want to acknowledge the entire Embecosm team, especially William Jones and Shane Slattery, which are working on this with me, and also our colleagues at Mosaic, which are supporting the work presented here. But yeah, thank you.